Hi everyone, my name is Jed Rothwell. I'm the librarian at the leonardkenner.org website, and I'm reporting today on excess heat from palladium deposited on nickel. Today's theme is replications and things that make me nervous. In 2019, Tadahiko Mizuno and I published papers describing experiments in which he detected heat from palladium rubbed onto nickel mesh. You can read the papers at leonardkenner.org, so I'm going to skip most of the details. This is air flow calorimetry, which is similar to water flow calorimetry, but less precise. Mizuno selected this method because his reactors are large and would not fit into a typical water flow calorimeter. Two reactors are placed in the chamber, the calorimeter chamber, the active reactor and the control. The chamber is insulated. Air enters at the bottom, warms up, and it goes out the top. The temperature difference multiplied by the volume of air and the specific heat of air gives heat. And here is one of the best results. Input was 50 watts of heating. 175 watts were captured in the airflow, and an estimated 75 watts were lost from the calorimeter chamber walls, bringing overall excess to around 250 watts. Now, in this case, you do not really need to estimate how much heat is lost from the walls. You can ignore that. Excess heat produced a temperature 11 degrees Celsius higher than the 50-watt calibration. In 2019, Mizuno and I distributed nickel mesh and detailed instructions to several groups of researchers in the United States and France. Unfortunately, they were not able to replicate the excess heat. We do not know why. These failed replications make me nervous. Could there be something wrong with Mizuno's calorimetry? 3 successful replications have been reported, one in India, one in China, and one at the Hokkaido University of Science, which is nearby Mizuno's lab. It was conducted by doctors Saito and Muto and 2 undergraduates, Igarashi and Nida. It's more of a collaboration than an independent replication. Mizuno gave them extensive assistance. I gather that Mizuno and the 2 professors assembled the equipment, and the students monitored it, compiled the data, and wrote the report. Mizuno said they did a great job. They watched it like hawks. Here is their equipment. You can't tell from the photograph, but this is much better than Mizuno's equipment in a building with better environmental controls, which is important with this kind of airflow calorimetry. This experiment is now being done by Muto alone. He's not been able to work for the last several months because of the pandemic, and also because he broke his leg playing rugby. This is remarkable because he's 72 years old. It's hard to say whether this is admirable or stupid, but it is remarkable. It is also emblematic of cold fusion because he is an old man playing a young man's game. This field desperately needs young researchers. They are more productive, they have more energy, more gumption, and they know how to use modern instruments. Well, in December, Muto was finally able to get back to work, so we hope to see some new results soon. In the meanwhile, let's look at some results from 2019. This is the data for 200 watts. The top is the calibration, the bottom is the excess heat one. Let me explain this gap between the input power, the orange line, and the blue line. That's caused by heat losses from the walls of the calorimeter chamber. So this is uncorrected data. And here's the same 200-watt uncorrected graphs on the left, and on the right is the calibration corrected for losses. So the heat balance is 0. And the bottom right shows excess heat, both corrected, the blue line, and uncorrected, the gray line. And here's data for 345 watts calibration and excess heat. Here is 400 watts. Now you've probably noticed that for some reason the uncorrected data shows that excess heat captured in the airflow calorimetry is just a little bit higher than the heat lost from the walls. In other words, the blue line is just a little above the orange line in the lower graph here. This is the same for all power levels. Why? I do not know. Muto and Mizuno do not seem to know either. Apparently, it is a coincidence. Coincidences make me nervous. They make me think there must be some sort of error. When you correct the data, output heat considerably exceeds input heat, so maybe I should worry so much. Here is the data from 8 power levels ranging from 72 watts up to 750 watts. Again, the gray line in the middle is input power. The yellow line is heat recovered during a calibration, which is never as much as input power. The blue line is heat recovered during excess heat runs, and the orange line at the top is heat corrected for losses. Excess heat as a percent of input power ranges from 128% to 149% of input power. With cold fusion, excess heat usually increases at a higher temperature, but it does not seem to do that in this case. Another thing to worry about. When you do experiments, you should be nervous, and you should stay nervous. As long as we're fretting about this, let's look at another problem. The effect is usually very stable. It's too stable, really. This looks more like an instrument artifact than cold fusion. On the other hand, another test on the right here shows more fluctuations. Well, another thing that bothers me about this is that Muto is using the same kind of airflow calorimeter that Mizuno uses. I wish it was something different, like a Seebeck calorimeter, because that would negate the possibility of a common systematic error. Let me zero in now on one aspect of the calorimetry. This is the top of the calorimeter chamber. The air leaving the chamber goes through the blower and then through the paper cylinder here before it reaches 2 thermocouples. The air must be well mixed or you will read the wrong airspeed and get the wrong answer. To be well mixed, the air must be turbulent, not laminar. The air must be moving quickly, and the cylinder has to be the right shape. Mizuno confirms that the air is well mixed and the air flow rate is uniform across the face of that orifice by doing a traverse test. He places the hot wire anemometer he's got there right smack in the center of the orifice, and he measures the airflow speed. Then he moves it to this another spot, and another right next to the wall. And then these other 3, 5, 6, and 7, all 7 points produce about the same airflow speed. He confirms it's the same. So here are measures of the 7 spots with the blower operating at 1 watt. And they're all together, as you see. Here's the second set of 7 spots at 1.5 watts. Again, the points overlap closely. And the third set at 1.8 watts. The points overlap. And so on, right up to 5.5 watts. The higher the wind speed, the closer together the points are. Mizuno also confirmed that the air flow rate is uniform by using a different kind of anemometer. The left shows the hot wire anemometer that measures the flow rate at one small spot. The gadget on the right is a vane anemometer, which with a propeller that covers most of the surface of the orifice. The readings from these 2 instruments are close. Not exactly the same, which would be suspicious, but close. Here you see perturbations where he installed the vane anemometer in the tube midway through a test. It is best to use 2 instruments based on different physical principles, that is to say, different systems, because that way you can avoid making the same common systematic error. For example, when you use thermocouples, before the experiment, you should calibrate them in water and then in ice slurry, comparing them to a mercury thermometer. That's what Mizuno does. Now, one of the people trying to replicate Mizuno's experiment was unable to produce a uniform flow of air. His traverse test kept coming up with a 2 meter per second difference at different spots on the face of the orifice there. That's a huge difference compared to Mizuno. Yet his blower was the same make and model, and the tube looked the same. I don't know why it did not work. Some people concluded that because this other calorimeter was not working correctly, and because it looked the same, Mizuno's calorimeter might not be working. Well, this turns the purpose of a replication upside down. You have to start with the same instruments, and you have to confirm they're working right. Then you try using Palladium to see if an anomaly occurs. If you do not even get the instruments to work right in the first place, this is a non-replication. I'm going to call that a non-replication. To be sure, if Mizuno had not carefully checked the air velocity to be sure it was uniform with both the traverse test and the vane anemometer, this other calorimeter would have called Mizuno's results into question. In a useful way, too. It would tell us where to look for a problem. Well, the person doing this other experiment ended up devising a different kind of exit tube, shown here, with a muffler on it. This piece of his calorimeter was quite different from Mizuno's. Does that muffler mean this is not a replication? I don't think so. Not in my opinion. This is not a test of fluid dynamics. As long as both exit tubes work, it does not matter that they are different. With most replication attempts, the starting conditions were met. The instruments were shown to work. Calibrations produced a heat balance of 0 after taking into account losses from the box. Unfortunately, the nickel-palladium samples did not produce excess heat, so I would call that a failed replication rather than a non-replication. A failed replication might indicate that Mizuno is doing something wrong, but it cannot tell you what his mistake might be. So far, no one has found a mistake in Mizuno's calorimetry, as far as I know. That's not to say we can be certain he did not make a mistake. We know the airspeed is not a problem, but maybe he did something else wrong. In one of his previous experiments with adiabatic calorimetry, he and I did make a mistake. We later did additional calibrations, we found the problem, and we published a retraction. As I said, in experimental physics, you must stay nervous. Keep worrying there might be a mistake, because there usually is a mistake. You can never be sure of a result until it has been replicated many times at high signal-to-noise ratios in many different laboratories. Here is what I consider an ideal replication. Fleischmann and Pons did the original experiment with half-silvered glass isoparabolic calorimeters, shown on the left. They called this particular one the Icarus model. The temperature is measured in the electrolyte with an array of thermistors. Some people suspected that mixing in the electrolyte might be a problem. Fleischmann and Pons did several tests which showed this is not the case. Well, Melvin Miles confirmed excess heat using the China Lake calorimeter shown on the right. This instrument is very different. It has a copper sheath all the way around the cell. And the temperatures are measured with two thermistors at two different locations on the copper. The two agree closely. Copper conducts heat well, so there is no temperature difference, and mixing cannot be a problem. Again, this system is different, so a systematic error common to both is ruled out. Well, Miles later worked at the NHE laboratory in Japan for several months. Fleischmann gave the NHE an Icarus calorimeter along with detailed instructions, which the people at the NHE ignored. Miles read the instructions, used the calorimeter, and again confirmed excess heat. Two different instruments, both showed the same excess heat effect. Other people have used flow calorimeters and Seebeck calorimeters. Very different. No systematic error. So what is a replication? What is a successful replication, a failed replication, and a non-replication? What can they tell us about the original experiment? A successful replication confirms the original observation and shows it is an anomaly. That's what Melvin Miles did. Mike McCoubrey says he's often recreated experiments reported by other people. He used similar instruments, achieved similar conditions, and measured the same numbers. But he found a prosaic explanation for these results. There was no anomaly. The original experiments were misinterpreted. This is also a successful replication, but no anomaly. In a failed replication, the researchers first show the calorimeter is working correctly. They try using palladium, but the effect does not appear. This might indicate that the original Fleischmann-Pons experiment was wrong. Indeed, it would indicate that, if cold fusion had not been so widely replicated. And in a non-replication, the prosaic original conditions are not achieved. The instrument does not work. The person who kept seeing different air speeds at different locations on the orifice was an example of that. Well, let me mention Mizuno's latest results. Mizuno may be observing a reaction with nickel and hydrogen only, without palladium. This is a preliminary result and power levels are low. I hope it is not an error, and I hope output can be boosted. This is my hope for two reasons. First, because nickel is abundant and cheap, whereas palladium is expensive, so this would make the technology more promising. Second, I would like to see this for nostalgic reasons, in memory of our late friend Srinivasan. He visited SRI and spent months trying to produce a cold fusion effect from nickel and hydrogen. He was frustrated and disappointed. In the end, he judged that he had not seen any significant positive results. It is too late to assuage his disappointment, but I would like to see that he was right after all. There are some good results with nickel, especially from biting. We need more replications, more. Well, let me conclude with some photos. Here's a cute picture of one of Mizuno's reactors being used as a room heater in the winter of 2018. This is the world's first cold fusion space heater. It is shown here without the power supply or deuterium gas tank. This one kept the room roughly as warm as a 3 kilowatt conventional heater. So by a very rough approximation, it must have been producing around 3 kilowatts. And here is a beautiful autoradiograph Srinivasan sent me. It shows tritium from a titanium disc that was used in a plasma focus device. That's a different kind of cold fusion. According to conventional plasma fusion theory, this experiment should have produced no more than 10 to the 9th tritium atoms, whereas in this experiment it produced 10 to the 16 tritium atoms. And you can read all about that in our special collection of papers from Bark. Well, that concludes my presentation about Mizuno's results. There are some references. I have a few minutes left, so let me show some of the search features at leonardcantor.org, a completely separate topic. The website has 1,127 documents and an index of 4,643 documents. That's a lot. So finding one can be difficult. So there's several ways to search for them, and here are 4 of them. First, the Google search box at the top of every screen, the library screen, some of the other indices, and the complete bibliography in EndNote export format. At the top of every page is a Google custom search box. This limits the search to files at Leonard Cantor only. This is what, let me show an example here. This is what we find for the search term Mercubri isoparabolic. Probably when you search for that, you're looking for that paper right there. The library screen shows a number of indices at the top. Most people use the one at the bottom there, where you search for an author, a title, or you do search all, which includes abstracts. Here I have done a search for the author Will and the title Tritium. Will is Fritz Will. You would have difficulty finding a paper by Fritz Will with Google because Will is a common English word, so you're going to find dozens of papers. I searched for Will in this example under all authors, not the first author, because I knew that he co-authored papers with his students. And this search, as you see, this search found 5 papers. The first 3 by his student. Another popular index is called the ASCII version of the complete bibliography. Peter Hagelstein likes to use this one. It looks like this. And you can do a Control F, for example, to find what you're looking for here. A search for tritium shows there are 716 appearances of that word. You can do a Control C and copy this whole document into Microsoft Word or some other program. And finally, we have the complete bibliography in EndNote export format. So you download this file. And there is a free online version of the EndNote program, so you upload the file into your copy, your own personal copy. EndNote is a nifty program used to, it's used to keep track of papers and to add them into paper as EndNotes. It has a relational database that is more powerful than the search function at leonardcantor.org. And as I said, you can use it to add titles to your own papers. Like this, like I've done here. The file you download from Leonard Cantor includes links to all of the papers. So you can include them in your bibliography if you wish to. And that's what I've done here. This concludes my brief look at the leonardcantor.org search features. Thank you very much.